In this video, I'm going to discuss the DC analysis of a common emitter amplifier. The transistor I have used in this example is an NPN bipolar junction transistor. This transistor has three terminals. The terminals are the base, the collector, and the emitter. It is important to realize that for an NPN bipolar junction transistor, this arrowhead always points outwards. In the common emitter configuration, the emitter terminal of the transistor is common to the entire circuit, and in this case is connected to ground. In addition to the transistor, there are two resistors in the circuit: the base or bias resistor RB and the collector or load resistor RC. The circuit is powered by a 9-volt DC source called VCC. The resistor RB sets the base current which flows into the base terminal of the transistor Q1. Let's call this current IBQ. It is important to realize that this base current IBQ does not change over time and is therefore known as the quiescent base current. The transistor Q1 then amplifies this small base current. The amplified current flows into the collector through the collector resistance RC. Let's call this current ICQ. The ratio of the collector current to the base current is called the common emitter current gain. The common emitter current gain is usually denoted by the Greek letter beta. We can think of beta as the amplification factor by which the transistor Q1 amplifies the small base current into the much larger collector current. The value of beta for a given transistor can be obtained from the manufacturer's datasheet. The transistor we have used in this example is BC547B. The BC547B is a general purpose transistor which is suitable for use in the driver stages of audio amplifiers. The beta for the transistor BC547B is around 300. Generally, circuit designers set the quiescent collector current ICQ such that the voltage dropped across the load resistor RC is half the supply voltage. Here the collector voltage is denoted by the node name VC. So the quiescent collector voltage is designed to be half the supply voltage VCC. Let's call the quiescent collector voltage VCQ, and it is designed to be half of VCC. As the emitter is grounded, the voltage across the collector and the emitter is also going to be VCC over 2. This is the ideal case in which the output can now be driven an equal extent in both directions. So if we were to apply a small signal AC input voltage, say from a microphone, the audio signal will modulate the base current and the amplified collector current will produce a corresponding output voltage without any distortion or clipping. The input capacitor Cin blocks DC and only lets AC signal through so that the DC quiescent bias conditions of the amplifier is not affected by the input audio signal. This capacitor is sometimes called a DC blocking capacitor or a coupling capacitor. For this circuit to function as an amplifier, we have to ensure that the base emitter junction is forward biased and the base collector junction is reverse biased. So VBE, or the voltage across the base emitter junction, should be greater than 0, and VBC, the voltage across the base collector junction, should be less than 0. If we satisfy this condition, then we will ensure that the transistor Q1 is biased in the forward active region. This is a prerequisite for the circuit to function as an amplifier. Let's now try to find the DC solution of the circuit. The DC solution is also sometimes known as the operating point. So our objective is to find the quiescent base current, the quiescent collector current, and the quiescent collector voltage. We know that the beta for the transistor BC547B is around 300. I also mentioned that in order to ensure that the transistor is operating on the forward active region, the base emitter junction needs to be forward biased. If we apply a voltage of 600 millivolts across the base emitter junction, we will turn on the base emitter diode and the base emitter junction will be forward biased. So VBE on is set to 600 millivolts. As the emitter is grounded, the base must be at 600 millivolts. Our first objective is to find the value of the quiescent base current IBQ. Since we know the value of the base voltage VB, the supply voltage VCC, and the base resistor RB, we can determine the quiescent base current IBQ by applying Kirchhoff's voltage law across this network. By applying KVL across loop 1, we can write VCC equals to the voltage dropped across this resistance, which is IBQ RB, plus the voltage across the base emitter junction, which is equals to VBE on, I have mentioned that the base voltage is equals to VBE on. That is because the emitter is grounded. We can write VBE as VB minus VE. Since VE is equals to 0, VBE equals to VB. So VB takes the value of VBE on. We can express IBQ as IBQ equals to VCC minus VB divided by RB. Now all we need to do is substitute the values of VCC, which is 9 volts, VB, which is 600 millivolts, and RB, which is 560 kilo ohms, and we can determine the value of the quiescent base current IBQ. So the quiescent value of the base current IBQ equates to 15 microamp. I'm getting rid of some of the clutter to make more space. So we have found out the quiescent base current equals to 15 microamps. We know that the quiescent base current IBQ will be amplified by a factor of beta by the transistor Q1. This amplified current would flow through the collector resistance RC into the collector node of the transistor Q1. So the quiescent collector current ICQ is given by beta, which is 300, times the quiescent base current, and this equates to 4.5 milliamps. So ICQ equals to 4.5 milliamps. Finally, we need to determine the quiescent collector voltage, which is the voltage in this node. The voltage at the collector node, Vc, can be determined by applying Kirchhoff's voltage law on this network. So by applying KVL on loop 2, we can write VCC equals to Vc, which is the voltage at the collector node, plus ICQ times the load resistance or the collector resistance RC. So Vc equals to VCC minus ICQ RC. We know the value of the quiescent collector current ICQ, which is equals to 4.5 milliamps. We know the value of the collector resistance RC, which is 1 kilo ohms. So we can easily determine the collector voltage. This equates to 4.5 volts. So VCQ is equals to 4.5 volts. Note that the value of 4.5 volt for the quiescent collector voltage is exactly half the supply voltage of 9 volt. And as I mentioned previously, this ensures that the output at the collector node can be driven an equal extent in both directions of the quiescent collector voltage. So we have now determined all the three parameters for the operating point. By determining these three parameters, we can find out the power dissipated by the transistor. We know that power is given by the product of voltage and current. We can determine the power dissipated by the transistor Q1 by taking the product of the quiescent base current and the base emitter junction voltage plus the product of the quiescent collector current and the quiescent collector voltage. So the power dissipated by the transistor Q1, P equals to IBQ times VBE plus ICQ times VCQ. We can usually ignore this first term here. This is because the base current is much smaller than the collector current. So the product of the base current and the base emitter junction voltage would be much smaller than the product of the collector current and the collector voltage. So we can write the total power dissipated by the transistor as approximately equal to ICQ times VCQ, which is approximately equal to 20 milliwatts. So this concludes our DC analysis of a simple common emitter amplifier. Before I finish, I want you to note that this simple common emitter amplifier has a major drawback. If we were to build this circuit using variety of transistors, we would observe that we get a different result each time. This is because each manufactured transistor has a slightly different common emitter current gain, or beta. Beta can also vary wildly across different batches of manufactured transistors. If beta varies, the quiescent collector current and the quiescent collector voltage will also vary. The quiescent base current does not vary because it is not dependent on beta. In the worst case scenario, if beta were to take a value of 600, then the transistor would draw a large amount of current. That is, the collector current would be very large. This would result in the collector voltage to be very small, much smaller than 4.5 volt, which will result in the base collector junction diode to be forward biased. And if the base emitter junction is also forward biased, then the transistor will go into saturation region and will stop functioning as an amplifier. The way to solve this problem is to use negative feedback, and I'll discuss that in my next video. Thank you for watching.